Welcome to lecture 21 of the course Computational Hydraulics. We are in module 2 numerical methods, and in this particular lecture class I will be covering unit 17, that is mesh free method, polynomial interpolation method. Learning objective of this particular unit: at the end of this unit, students will be able to discretize ordinary differential equation using polynomial interpolation method. Polynomial interpolation method, function phi can be represented at a point x with the approximation as phi h starting from j equals to 0 to m. This is p j x a j x, and we can represent it in terms of vectors like p transpose a. So, in this case we can use the concept that we have learned in our previous lecture class. This is p transpose, which is nothing but for one dimension this is 1 x square up to x to the power m. That means we will have m plus 1 number of terms here. Similarly, in this case we have x y 1 x square x y y square, and this expansion is there. So, for n plus 1 nodal values for phi 0 we can have a 0, a 1, p 1 to p n, and phi 1 this is phi n. Similarly, we can represent. So, starting with this we have n plus 1 nodal values. Similarly, we have m plus 1 polynomial function values, or a in this case. So, let us use this for our calculation. We have represented these nodal values, n plus 1 nodal values, in terms of a and p. Now, if we write it in the form of matrix, we can write this like phi, which is column vector. Again, p is a matrix. This is our size of n plus 1 into 1, and p is of size, this is our m n plus 1 into m plus 1, and we have this a, again this is m plus 1 into 1. So, with this we can start our calculation. We can get for n plus 1 equals to m plus 1, we can invert this matrix. So, in this case we can get phi, which is our field variable in terms of P transpose A x. So, P transpose, if you replace this A from this equation, we can get P inverse phi. So, we can represent this first portion P transpose P inverse m plus 1 as W transpose, which is our weight function, and phi is individual function values. Now, W is a vector of shape functions, where W transpose, this is our original thing. So, W 0, W 1, W 2 to W m. Now, in case of our groundwater flow in one dimension, this was the problem definition. We have seen the discretization using finite difference and finite volume technique. Now, let us see how we can utilize the same problem, and we can utilize our mesh free method to discretize the governing equations. So, mathematical conceptualization is clear. We have d2h dx2, and this is a right hand sourcing term, and Dirichlet boundary on the left hand side. Right hand side we have Neumann kind of boundary or zero Neumann boundary condition. The domain discretization, within this straight line from starting from 0 to L, we can generate number of points x 1, x I, x minus I, x plus I, x n, these nodal points. Now, we can use these nodal points for our calculation. Let us say that for x I, this is our support domain. So, we have x I minus 1 and x I plus 1 within the support domain. In case of numerical discretization using mesh free shape function, h can be approximated as h, which is W transpose h. So, in this case we can also approximate the derivative. So, in calculation of the derivative we can differentiate the weight function or shape function. Again we can differentiate this W transpose or the vector of shape function. Hs is the vector that collects the nodal values of the unknown functions. W I transpose, in general it should cover all the points, and Hs also it should cover all the points, but we have limited our support domain to the adjacent nodes only. So, n plus 1 number is the nodes used in this case. So, ns is the number of nodes present in the local support domain. So, we can have 1 into ns, and for interior point xi, governing equation can be obtained like this. So, this is our differentiation or first term. We can directly write h as hi for the center node, and right hand side we have hwt, which is again varying with xi. Now in this case we can define our polynomial basis of order 2 where we have 3 terms 1 x and x square. This is one dimensional problem, that is why we are only using x in this case. So with this we can calculate the weight function. So this is nothing but P transpose x, this is d2 dx2 of this, and this is P inverse ns points in the support domain. So with this we can write that this is 1 which is coming from here, again x which is again from support domain, x square from here, this is coming. Now we have to differentiate it twice to calculate this one, and we are writing this inverse thing. This is P0, P1 and P2. So we have 3 points within the support domain including the center node, because if you have I minus 1 and I plus 1, then we will have 3 rows and 3 columns here, because we have considered 3 terms in the polynomial basis. So with this if we proceed, interestingly we can see that the second order derivative is 0, second order derivative is 0, only coefficient that we are getting is 2. Now x I minus 1, this can be represented as x I minus del x, considering we have uniformly spaced nodes available within the domain, then x I equals to x I and x I plus 1 equals to x I plus del x here. Now with this simplification, if we use in this case, we will simply get this 1 by del x square, this d2 w transpose dx2, this will be 1 by del x square minus 2 by del x square 1 by del x square. Interestingly, whatever we have got for our finite difference and finite volume case for this particular problem for interior node discretization, we have exactly got the same thing. Ns equals to 3. Now we have symmetric support domain. Now this is interior equation for ith node, and governing equation is used for only interior points. Now let us consider for right boundary. Right boundary, again we have n, n minus 1, n minus 2. So with this if we calculate, that means in polynomial basis we have 3 members, and in this case also we have 3 nodes, that is I minus 1, I minus 2 or n minus 1, n minus 2. So in this case again x I minus 1 equals to x I minus del x, x I minus 2 equals to x I minus 2 del x. So if we use this approximation for our case, then and this is again 0, this is 0 and this is 2. With this approximation, the coefficients this is 1 because this is first order derivative, this is 0, this is 1 and this is 2 x I for ith node. So, if we simplify this one this inverse thing, then we can get 3 by 2 del x minus 2 by del x. If we multiply this with 2, this is 4 into 2. Interestingly, whatever boundary condition we have used for one sided finite difference approximation for first order derivative for second order accuracy, this is same thing we are getting from mesh free method. Now, we can directly use this approximation for right boundary. So, 3 h n minus 4 h n minus 1 plus h n minus 2, and for left boundary we have directly h 0 equals to h s or specified value in this case. So, we can construct our matrix for n s equals to 3, again that will be banded matrix, but this one dot will be extra because we have extra term available in case of right hand boundary condition with our 0 Neumann case. So, we can use the full matrix, or we can use finite difference like approximation in this case, and we can include only 2 points near boundary for our calculations. But obviously, in that case our accuracy will reduce for inclusion of only 2 points during calculation. So, we can directly invert the matrix and get the solution from this calculation. Thank you.